Without equations, I want to try to explain the concept of magnetic flux and how that relates to the concept of induced current. So first, let's start with the concept of flux. Flux is essentially if you have a particular surface, then if you have something like a field where you can have lines and the density of those lines tell you how strong the field is. We see this both for electric fields and for magnetic fields, that if the lines are closer together, that suggests that the field is stronger than when the lines are more spaced apart. So essentially then, flux is a measure of how many lines are going to go through a surface. As I often do, I like to start with something that is a little bit more intuitive to us, which is the idea of water and the idea of water flowing. It's definitely more intuitive to us than these tiny electrons that are much smaller than our everyday experience. So bear with me for a second, because I want to develop flux first by trying to think about if you had a river. So let's say the river is flowing horizontally on the screen. And so I could depict the flow of water in that river with a bunch of streamlines. Imagine a bunch of like parallel lines, right, that are pointing in the direction of the motion of the river. And the density of those lines, how close they are together, would be a proxy for the speed of the flow. Okay, and so essentially, now imagine that I have like a hula hoop. Okay, pretend this is a hula hoop. And so essentially what flux is we're going to try to catch lines. Okay, in the case of a river, it's streamlines. And as I'm going to explain in a moment, when it comes to a magnetic field, it's trying to catch magnetic field lines. So again, so imagine the river's flowing, right? And so you have a bunch of these lines. And so the objective is, how would I orient my hula hoop to maximize the number of lines that pass through it? So this is my surface, okay? So if the river is going like this, if I oriented my surface like this, it wouldn't be catching any lines. It would be parallel to all the streamlines. The water would be flowing right past it. It wouldn't be going through it. So this is where the flux would be zero. Now, as I start to orient it more and more and more and more and more and more perpendicular to the field lines, we're having more and more flux of water going through the surface. And so it's the same thing with magnetic fields. Okay, imagine I had a magnet. Imagine this hand is a magnet. Let's say that this side of my hand is the North Pole and this side is the South Pole. And so you can imagine that the field lines are going to leave the North Pole, they're going to circle around and go to the South Pole. So towards the top of the magnet, right, at the North Pole, the field lines are more concentrated. Okay, so imagine I have a magnet. I've got field lines that are emanating from my magnet. And imagine I have, say now, not a hula hoop, but imagine it's a coil of wire. Okay? And so now, let's say that I take my coil of wire and I start moving it closer and closer to this north magnetic pole. Now, in the wire, okay, there's charges. And there is a magnetic field by the presence of that magnet. And so then if I start moving my charges with some velocity v, if you remember, if you have a charge that has a velocity in a magnetic field, then we have a magnetic force. We call it the Lorentz force law. That was the whole thing where you have to consider the charge, the velocity, and the magnitude of the magnetic field. So again, if I have a magnet, I have a coil, and I now give the charges in that coil some velocity in a magnetic field, those charges are going to experience a force. And so if those charges are experiencing a force in the wire, that means the charges are going to start moving in the wire. They're either going to go in this direction or that direction. Okay? And so this is what we mean by an induced current, is that if you have charges in a coil of, say, copper wire, you have the presence of a magnetic field, and there's a relative velocity between the two, then there's going to be forces on the charges that are going to make them either go in this direction or that direction. And so now what I want to explain without equations is how you can think about what direction the induced current is going to go. And so this is sometimes called Lenz's law. And the basic idea is that Mother Nature does not like changes in magnetic flux. Okay? Again, Mother Nature is not a fan of changes in magnetic flux. So like, for instance, if the magnet was just sitting here and the coil is just sitting here, there's no change in flux, right? You have the same amount of magnetic field lines that are going through the coil. But if I start moving this closer and closer, more and more field lines are going through the coil, which means the flux is changing. In this particular example, as the flux is changing, it's changing in that direction. Okay, so the change in the direction of the magnetic field line flux is in this direction when I move the coil closer and closer. Mother Nature doesn't like this change. And so Mother Nature has an induced current in the loop that creates its own magnetic field that opposes the change in flux. So again, if the coil gets closer and the change in flux is this way, then the induced current is going to want to create a magnetic field that goes in that way. It goes opposite the change in flux. And so to determine which direction it goes to create a magnetic field that goes opposite the change in flux, we have to use the right-hand rule. So if it went like around like this, if I curled my hands, the magnetic field would be going in the same direction as the change in flux. So that means that instead it's going around like this. And so right-hand rule, when I curl through, the magnetic field is going this way, the change in flux is going this way. And so if I was to hold the magnet and move this coil closer, there would be a current in the loop, and it would be going in this direction to oppose the change in flux. Why is it that way? If it was the other way, we could create perpetual motion machines. So think about it, like if I had a magnet right here, and this was a North Pole, okay? And then when I move it closer, if I have an induced current, it's going to have its own magnetic field that it generates. So if it goes in this direction by the right-hand rule, it would mean that the flux lines are coming out like this, which is to say that this would be functioning like a North Pole. So you'd have a North Pole and a North Pole, and that's going to want to go back like this, okay? And that's what happens. But let's say hypothetically that like when I move this closer, instead it goes in this direction. If it went in this direction by the right-hand rule, when I curl my fingers through, that would mean that this would be a North Pole and this would be a South Pole. So if this was a North Pole and this was a South Pole, then if I just barely nudge this, the induced current would create a South Pole here and a North Pole here, which would want to attract each other even further, which would create even more current, which want to attract even further. So all I'd have to do is this little nudge at the beginning, and I'd have this perpetual attraction. So you don't have perpetual motion machines in nature. You can't get something for nothing. That's the idea of energy conservation. And so that's why when there's an induced current in a coil with the presence of a magnetic field and the charges in that coil having a velocity, you have to think about the direction of the current, and the direction of the current is such that the magnetic field in the coil is going to be opposite the direction of the change in flux through the coil. So just think to yourself, what direction is the change in flux going? So one more time, if I move this closer, that means more and more magnetic field lines are going through the coil, which means the change in flux is this way. So that means I have to have an induced current that creates a magnetic field that points opposite the change in flux. And to do that, it needs to go around right-hand rule, curl through like this, right? So the magnetic field induced is this way because the change in flux is this way. And again, this all goes back to the concept of flux, which quite simply is if you have a representation like streamlines or like field lines, it's how many of those go through a particular surface, like a coil.